2, the molar enthalpy of formation will be 0. Calcium is a metal, okay, 0. And then graphite, most stable form, graphite, well, carbon at 0. But if you convert graphite into diamond, well, the enthalpy of formation is 1.88 kilojoules per mole. Okay. So you know diamond is not as stable as graphite, and thermodynamically, diamond is supposed to convert into graphite. Kinetically, that reaction is not favored because it takes forever for that process to occur in nature. That's why we have diamond exist in nature. And even though diamond and carbon, they're all diamond and graphite, they're all made of carbon atoms. There's really nothing so special carbon about diamond. It's just carbon in a different way. Carbon atoms connect to one another. So one thing to remember is that the elements in the most stable form, the enthalpy of formation or standard enthalpy of formation is always 0. Okay, and then for each compound that carbon can form, for each compound that involves the formation of bromine with bromine and calcium, and this is only a partial list of everything. So hydrogen, normally under standard conditions, hydrogen stays as the diatomic molecule. So the enthalpy of formation for hydrogen H2 is 0. But if you want to get hydrogen atom, you have to split up the molecule. When you split up the molecule there, you have to break that hydrogen-hydrogen bound. When you try to break that hydrogen-hydrogen bound, it takes energy. Okay, so hydrogen atom, the enthalpy, standard enthalpy of formation is 218 moles, kilojoules per mole. But hydrogen gas, H2, 0. Okay, so this is a table that will be given to you. If we ask you to do calculations, we'll give you this table there. You just need to know how to use this table to determine the different enthalpy of formation for a particular process. We'll give you an example here. So we ask you to calculate the enthalpy of formation for calcium carbonate. Okay. Now, calcium carbonate can be obtained from this chemical reaction. Calcium oxide, carbon dioxide, mix them together, you end up with calcium carbonate. Okay. Now, given the information there, well, the question is asking you, what is the enthalpy of formation for calcium carbonate? Given the enthalpy of formation for calcium oxide, negative 635.1. Carbon dioxide, negative 693.5 kilojoules per mole. Calcium carbonate, the standard enthalpy of formation for calcium carbonate, negative 1200 to 7.6 kilojoules per mole. We're asking you what is the overall enthalpy for this chemical reaction. Enthalpy refers to the amount of energy transferred. Well, energy is a state function. All we need to do is to add the enthalpy of formation, molar enthalpy of formation for calcium carbonate, and that's the product, minus the sum of calcium oxide and carbon dioxide. Going back to the table that we showed you here, calcium carbonate, we find this number. Okay. Calcium oxide, 634 points. I have 0.7 there, and this is 0.9. So you can see there's slightly different things. And then carbon dioxide, negative 393.5. Okay, so these numbers actually come from that table there. How do we figure out the enthalpy of this overall reaction? All we need to do is add them together. Okay, the molar enthalpy of formation of calcium carbonate minus the sum of the molar enthalpy of formation for calcium oxide, carbon dioxide. You plug in the number, you get the answer. Simple addition and subtraction. The number is given to you. Okay, so in the calculation part, in the end, I still remember vividly my experience when I take thermodynamics courses there, and when we are asked to figure out the enthalpy of reaction there, it's always confused. Which number do you add? Whether do you have a positive sign and a negative sign there? Well, keep in mind state function. State function only has something to do with the end state and the beginning state. The difference between the two. Well, if you can figure out how do you go from point A to point B? Well, what is point A? Well, the starting stage. And what is point B? The end stage. all you need to do is to add the numbers at the end stage, the final stage, and add the numbers together at the beginning stage, start point, and take the difference between the two. You end up with the enthalpy change for that particular process. Okay, so this particular reaction and this particular example there, and chemical reaction, molar enthalpy of formation. Now, again, this information, you can obtain that information from a table. If we ask you to do calculations in an exam there, we will give you these information there. You just need to understand how do we use the molar enthalpy of formation to figure out the enthalpy change there. The overall enthalpy change for the reaction is the difference between the total of the molar enthalpy of formation of the product minus the total of the reactants there. You get a simple addition and subtraction there. Nothing really complicated in this particular type of calculation. Now we said sometimes you need to reverse a reaction in order to do your calculation. And here is an example. If you have methane reacting with, natural gas, methane, reacting with oxygen, you burn methane in the presence of oxygen, you generate carbon dioxide and water. Okay. So this is the balanced chemical reaction equation. Now, if we ask you to calculate the enthalpy change for the combustion of methane, we can actually, this is the information I would give you there. Okay. From the molar enthalpy of formation, methane, CH4, you can assume that, CH4, you have carbon and hydrogen there. So carbon element plus hydrogen gas, you can make methane. You will be able to figure out the amount of energy involved in there. Given the molar enthalpy of formation for methane, you can determine the amount of energy involved when you make methane. But methane is our reactant. We're not making methane here. We're burning methane in the presence of oxygen. We're getting carbon dioxide and water. So here, we can actually say methane reacting with the oxygen gas there. And the first step is you decompose everything into its elemental form. That is, you separate carbon and hydrogen in methane, you get carbon, graphite, and hydrogen gas. Okay, so plus the oxygen gas there. And this is, here it's already a free element. So if you go from this is the reactant side of the overall reaction. If you go from the compound element into pure elemental form, okay? So this is the one step, the first step that you go. And then if you have carbon, hydrogen, oxygen, carbon and oxygen can combine together to form carbon dioxide. Okay? Hydrogen and oxygen can combine together to form water. Okay? So the overall process, and you can see, this is the starting point. Graphite, hydrogen gas, oxygen gas. We form carbon dioxide first. And then we form hydrogen, with hydrogen presence of hydrogen and oxygen gas, we form water. So that's an overall step. This is the overall step, step one, step two. Okay. But getting here requires you to break methane into its elemental form, carbon into hydrogen. Hydrogen, the most stable form of the element in the physical state at 1 bar at a specified temperature, 20-25 degrees Celsius. Hydrogen exists in H2. So you've got 4 hydrogens in there, 2 H2. Okay. Oxygen, oxygen is O2, diatomic molecule there, so 2 O2. And then it's a carbon, 2 hydrogen molecule.